Hi, welcome to the first video of the channel and the first video in the Smart Bulb series. So in this series we're going to be building one of these smart bulbs similar to what's made by brands like GE, your Samsung SmartThings, and even Google and others. So here's a basic list of design requirements that we're trying to go through. It's going to be red, green, and blue, so it's going to be able to change colors across the spectrum. It's going to be dimmable, so if you ever need to make the brightness low at night or change it based on mood or ambiance, you can do that. It's going to run about 7 to 10 watts, and we're trying to target something like 800 lumens. This is pretty average for a bulb. I try to make it a direct correlation to the ones that you can get on the market at about a $30-ish price point. We're going to do communication over Bluetooth, and that's going to handle the 2 and 4th of the commands from the phone or whatever ends up actually sending these commands to the lights to turn on and off. So the bottom here, this is a ballast or a base, and this is what screws into your light fixture. In America, this is an E26. In different countries, it might be something else. Above here, the protective casing. Right here, at the top, you get your LEDs. This base is mainly aluminum that you can see, and the power management board kind of sits in a groove over there, and that connects to this metal plate. So the main reason for it being aluminum is for heatsink purposes. Now, a main characteristic of a light emitting diode or an LED is that it's temperature dependent. So if you have something like a bulb where you're trying to get these LEDs to have a consistent color temperature, to have them consistently output the same intensity of light over the course of the day. So even as they've been running longer and the electronics might be getting hotter, you don't want your LED to start dimming or to now have a different shade of yellow or white or whatever it was supposed to be. They will decide what kind of power supply we're going to be picking, but the most important part of any bulb really is to take your AC signal coming in from your wall, convert that to a DC signal, because LEDs run off of DC voltage. In our case, not only will it handle that AC to DC conversion, it will also handle the actual communication to our probably mobile phone or other controlling instrument to turn the lights on or off or to change various color settings or things. So once that AC to DC is converted, it will also handle communication, but even if it wasn't, you have a stage called an LED driver. They make a lot of chips specifically for this purpose. I haven't looked into what I want to do for that part of the circuit, but essentially it's taking that DC voltage and making sure that all these LEDs here are getting a constant current and they're all getting lit equally. This AC to DC conversion happens in 2 steps essentially. Your first step, well, I guess it's kind of 3, but the main 2 steps. So your first stage is a rectifier. And your rectifier is taking your AC signal, the sinusoid has a positive and a negative amplitude. It is essentially converting that to be only in the positive domain. So using a H-bridge or a full wave rectifier, it has 4 diodes connected in that particular configuration, and they only allow a positive signal to pass through. Stage 2, something called regulation, because that earlier rectified signal that we have, it's got these little bumps, and we want to make sure that we have a straight DC line. Regulators are mainly of 2 types. Your first type is a linear regulator. Your second type is a switch mode regulator. And here's what they look like. So your linear regulator here, running off of an op-amp with a closed feedback loop. So that feedback loop and the resistances that we set it to can set your regulator to be a constant output. So your switch mode power supply looks something like that, and it has an inductor or rather a transformer. By changing the duty cycle, so duty cycle is how long the duration of which your signal is on and off. So by changing that wave, we can change the charge on the load, so you're able to change or control the output voltage by changing simply how long your transformer is on or off. And this is how they stack up. So in terms of safety, your switch mode power supplies are far safer Now, it's not that linear supplies can't be that they aren't safe, or that they can't be made have certain groundings and just to make sure that you don't electrocute yourself. It's just that switch mode power supplies rely on a transformer. And what that means is, you have your two plates, they have what's called galvanic isolation, so that there's a physical separation from the two plates of your transformer. And that means that your AC signal on one side does not interfere with your DC voltage signal on one side. So having that difference and separation within your circuit itself means that it's not going to carry over to another side. In terms of efficiency, switch mode power supplies are known to be very efficient, and about like 90 to 95% efficiency in terms of the input power versus output. So in that conversion process, it is barely losing any power, and that is very good for us. For a linear supply, it goes to about 35 to 50%. You can expect about 50% efficiency in a linear power supply, but if you think about that in terms of bulb, half of that input power that's going in is getting wasted in terms of heat. So it's just letting that go. That's just how it works. It's problematic for us because not only is it inefficient to be wasting half of the power that you're consuming, but that other half is being let go as heat. And when we have our little bulb here in that small space, more heat is not a good thing for us, because that just means we got to handle that heat better. In terms of EMI, now this was a big one, and it can be mitigated in a switch mode power supply. Linear supplies run very smoothly and they generate almost negligible electromagnetic interference. But because we mentioned that the switch mode runs off a transformer and it runs off a pulse width module, that alternating signal that goes on based on its duty cycle, that generates a lot of electronic noise. And that noise is emitted at certain frequencies, and while these frequencies aren't high, 2.4 gigahertz that Bluetooth transmit over is a very high frequency. So we're not expecting something to interfere with there, but I don't know enough. I don't know enough to say that for sure, and I haven't tested it. So we're going to add precautions in our design to filter out those frequencies, and I don't see it really being a big problem if we make sure to include it from the beginning. So next time, we're going to simulate the switch mode power supply. We're going to make sure we have that part of the design done, and then we're going to look further into how to build this LED driver and look a little bit into the communication. I've never actually had a discrete microcontroller or a Wi-Fi or Bluetooth module integrated as part of the design. I think the size is also going to be something interesting. So after we get into the driver and we start getting into the communication, that's stuff I haven't really tackled. So that's going to be tough, and we'll see. I'm going to learn a lot out of it, and hopefully it'll work. So thanks for watching video 1.